This module is going to introduce the idea of probability distribution, leading into understanding or the introduction to one of the most famous continuous probability distribution that exists, the standard normal distribution. Okay, before we get there, we're going to start off talking about discrete probability distributions that are organized in tables. So just like when we first started talking about the different variables we can have in statistics, we could have quantitative variables that are discrete or quantitative variables that are continuous. When we think about our variables for probability, again, they can be discrete counts or they can be continuous measurements. So we'll start off looking at discrete because, again, they tend to be a little bit more straightforward and something we're familiar with. So we might consider thinking about all the different possible outcomes for probability questions. So we might have look at the probability of the average number of female moths among 14 moths in general. So clearly in a group of 14, we could have 0 females all the way up to 14 female moths. Okay, and then we can organize the probability of each outcome in a table. In one column, we have the outcome listed, and then in the other column, we see the probability listed. Again, a full probability distribution will list all the possible outcomes in the table. Okay, based from reading that table, we can answer all sorts of different questions. So what's the probability that there are exactly 6 moths? We'd write that using probability notation. The probability that x is equal to 6 is equal to, and we could get that number from the table. No math required. Okay. The next example in our notes, we've got the probability that x is, and then we see this symbol, okay? We might recognize that that symbol is less than or equal to. So what's the probability that we have 2 or fewer moths is another way we could think about that question. And so to figure that out, we'd have to look at, well, what's the probability that we have 2 female moths or 1 female moth? Or no female moths. Adding those up, we get our answer is 0.007. Okay. We might be interested in what the probability is that x is, and this is strictly greater than, that we have more than 14 moths, not including 14. So because the most we could have is 14, then the probability that we have more than 14 is 0. And similarly, the probability that we have less than or equal to 14 is going to be 1. It's a sure thing, right? Remember, and this is a key thing we have to remember about probabilities, is the sum of, sorry about that, sum of all probabilities in a distribution must be 1. Okay, excellent. So let's go on and look at some other examples. So again, just like table of values for data organization can be useful, but a visual representation is also great. So it's pretty common that we'll see probability distributions that are changed from being in a table to a bar chart or a histogram. Okay, so in this example, we want to figure out in a group of X students, what's the probability, or in a group of 4 students, what's the probability that X exercise regularly? So we could ask, what's the probability that no one recognize? 1, 2, 3, or 4. And if we know 65% on average exercise regularly, then we could calculate all of those different probabilities that are listed in the table, right, using our tree diagram or some other method. But we've looked at how to calculate those probabilities using different probability techniques. So they could be determined using a tree diagram. perhaps, right? But we organize a summary of all of the different possible outcomes in the table, and we could show it visually in a bar graph, okay? And so along the x-axis, we see all the different possible outcomes, and then the probability is up the vertical axis. Okay. So just a little practice question here. Working backwards now, you have a probability distribution chart given to you. Reading from the chart, create the probability distribution table, and then answer the question, okay? So pause the video, try that out, and then check your answer. Okay, so the different possible outcomes that we have are 1, 2, 3, 4, 5, or 6. The probabilities for each are listed, and the probability that we roll a 4 or higher is the probability that we roll a 4 or a 5 or a 6. We can add those probabilities together, and the answer is 0.5000. Okay, wherever possible, we'll keep in the habit of reporting our probabilities to 4 decimal places. Okay, so all the probabilities distributions we've looked at so far are discrete. They've dealt with counts of things or numbers being ruled, and so we can create an exhaustive list. But a lot of the measures that we're interested in finding probabilities for might be for continuous variables. The probability that someone's height is between 160 and 170 centimeters tall. The probability that somebody's blood pressure is between 120 and 140, right? And they could be any number in between, including decimal numbers, okay? So before we move on, again, think about these 4 examples: the weight of a quarter pounder burger, the number of burgers somebody eats, the amount of time you spend waiting on a bus, the number of eggs laid by a chicken each day, and think about, are those particular variables discrete or continuous? Because again, our techniques that we use for statistics vary depending on if the variables we're dealing with are discrete or continuous. So the answers are continuous, discrete, continuous, discrete. And again, like before, when we have continuous variables, it's really important to think about the units that we're being measured in, right? Whereas discrete values are numbers or counts and tend not to have units associated with them. So when we have continuous variables, such as time, then we can't make a bar graph or make any sort of chart of all the possible outcomes. But what we can think about is a range of values that the outcomes might fall between. And then the probability graph that we have is called a probability density function. And we calculate probability by finding the area underneath the probability density function. Okay, most of the time, we need technology to help us out, but the exception for that is the continuous uniform distribution. So when we have a range of values that all have the same probability of recurring, then because the area is a rectangle, we can easily calculate the area and the probability manually. Okay, so let's look at this example, including a bus. So a bus goes by a bus stop every 12 minutes. If we show up at random, we can figure out the probability that we wait a certain amount of time. Okay, the probability density function has a height of 0.0833. How does it get that height? Well, it's given because the total area, the total probability that between 1 and 12 minutes has to add up to 1, then the height is given by 1 over whatever the total range is. So in this case, it's 1 over 12, which turns out to 0.0833. Okay, so if I want to know the probability that I wait between 3 and 8 minutes, I could write that as, so the probability that my x value is greater than or equal to 3 and less than or equal to 8. And I'd find that by thinking about the area underneath my density curve between 3 and 8. Again, that's a rectangle. That particular rectangle has a width of 5 and a height of 0.0833. 5 times 0.0833 comes out to 0.4167. So my probability of waiting between 3 and 8 minutes is about a 41.67% chance. Okay. If I want to know what the probability is that I wait less than 2 minutes, then, well, I can't wait no minute. I have to wait at least some time, right? So probability that I'm waiting between 0 and 2 minutes, I can find by thinking about what my base value is and my height value is, multiplying those out, and I get 0.1666. So I've got about a 16% chance of waiting less than 2 minutes. Okay, so there's a bit of an introduction to their different probability distributions for discrete and continuous variables. And the next part of our notes is going to introduce, again, the most important continuous probability distribution that we're going to come to know, and that's the standard normal probability distribution.